Hello, my name is Gamal El-Komi. I'm a PhD student at the University of Tartu, Estonia. In this video, I am presenting the paper entitled Secure Multi-Party Computation for Inter-Organizational Process Mining. Process mining is a family of techniques for analyzing business processes based on event logs extracted from information systems. A large number of business processes are happening between more than one business organization. In such a case, each of the cooperating organizations has its private event log. Organizations are unwilling to, or sometimes illegally prevented from, sharing detailed event logs. The cooperating organizations would hire a data analysis firm to analyze this collaborative process in view of detecting bottlenecks in the process and recommending changes to the process to increase its efficiency. The organizations don't trust the data analysis firm or any other third party to the extent that they would share their full event logs with them. Besides, this might not be possible due to privacy regulations. In practice, many business processes involve multiple independent organizations. We call such processes inter-organizational business processes. An example of such process is the process of ground handling in an aircraft. The process involves two parties, the airline and the airport. Each party has its event log for the activities that happens on its side. Both parties want to optimize the process, but neither of them is willing to exchange their private data due to privacy regulations. In this paper, we introduce a secure multi-party computation framework for inter-organizational process mining. The framework allows Party A and Party B to control what is disclosed and what is not. In this paper, we assume that Party A and B have agreed to reveal the result of analysis queries, but nothing more. In other words, neither Party A nor Party B will learn anything about each other's data, but only the result of the performance analysis queries. Due to legal development such as GDPR, existing research discussed the necessity of privacy-preserving process mining. Some techniques adopted anonymization of event data, like using k-anonymity and t-closeness, to achieve privacy-preserving process mining. Other techniques try to directly incorporate privacy considerations in the process mining techniques. The problem of automated discovery of process models in an inter-organizational setting has been considered. However, these approaches don't address privacy concerns. Also, some techniques are proposed to compare the same process across multiple organizations. The problem of ensuring privacy in inter-organizational process mining has been discussed by Leo et al. They provided a process mining framework based on the assumption that the parties in the process are willing to share the confidential information with a trusted third party. Secure multi-party computation is a cryptographic functionality that allows parties to evaluate a function together, with no party learning nothing besides their own input and output. Homomorphic secret sharing is a common basis for multi-party computation protocols. In such protocols, the arithmetic or Boolean circuit representing the functionality is evaluated gate by gate, constructing secret shared outputs for the gates from their secret shared inputs. Each evaluation requires some communication between the parties. Several frameworks support such deployment of multi-party computation and provide APIs to simplify the development of privacy-preserving applications. One of such frameworks is ShareMind, whose main protocol set is based on secret sharing among three computing parties. In this paper, we build on top of ShareMind, but our techniques are also applicable to other secret sharing-based multi-party computation systems. ShareMind provides its own programming language, the secrecy language, for programming privacy-preserving applications. Secrecy allows us to abstract away certain details of cryptographic protocols. In this paper, we use three-party multi-party computation protocols which are secured against honest but curious adversaries. We assume that the input parties are sharing only the number of activities and the maximum trace length in their event logs. Even with the encrypted data, contextual knowledge might lead to leakage of some information. For example, an adversary might learn the shortest or longest trace, and with domain experience, they can reveal the actual activities. For such a case, we perform padding to make all the traces with the same length. Another leakage might happen due to frequent pattern mining. We use privacy-preserving quicksort algorithm, and also we use one-hot encoding with the privacy-preserving outer product to update the DFG matrix. We consider a model in which an event log is defined as a set of events, each capturing a single execution of an activity at a specific time, as part of an instance or trace. For an inter-organizational business process, an event log that records the process execution from start to end is commonly not available. Different parties record sublogs based on events that denote activity execution at the respective party. We assume that each activity can only be executed by one of the parties. Also, we are considering the general case where the handoffs of the logs are not calculated and both parties want to calculate the joint process model based on their event logs. To realize this scenario, Party A and Party B import their event logs into their respective clients, which are under their control. The client of each party converts the logs into secret shares, then imports the secret shares to ShareMind servers. Meanwhile, a third ShareMind computing node only exchanges secret shares with the servers of Party A and B. The steps of calculating the DFG matrix, like sorting, updating the matrix, are being performed securely using secret shares. To calculate the DFG matrix, we combine the event logs from both parties into a single log that represents the event log. After that, we need to determine which events follow each other in a trace. We do that by grouping the events by their trace identifier and ordering them by their timestamp. Since the trace identifier is secret shared, we cannot group the events directly. Instead, we use privacy-preserving quicksort algorithm to sort the event by their trace identifier. We do the same with timestamps. We perform the sorting using divide and conquer technique for faster processing. Then, we calculate the DFG matrix inside the multi-party computation platform. Since the information on the activity of an event is secret shared, we can't simply process the events of traces sequentially. That would be vulnerable to the pattern mining attack. We adopt a one-hot encoding for activities so that each activity is represented by a binary vector. We use the outer product of such vectors to calculate masks to filter out all the other matrix entries and enables only the update of the entry corresponding to each two activities. As soon as the DFG matrix is ready, the query engine can reveal the results of the queries to the user. We define the queries as a subset of the annotated DFG, which limits the amount of information each party can learn about the process. The source code of our implementation is available on GitHub. Also, the repository contains the installation steps, dependencies, and event logs. You can access the repository using this link here. We conduct feasibility and scalability experiment specifically to address how do the characteristic of input event logs influence the performance of the secure multi-party computation of DFG. What is the effect of increasing the number of parallel chunks on the performance of the multi-party computation of the DFG? We used real-life event log of intra-organizational processes comprising logs of varying sizes and characteristics. We tried to simulate the inter-organizational processes setting using the datasets. We selected 3 event logs. First one is PPIC 2013, which captures the problem of management process at IT department of a car production company. It is an example of a small event log. The second one is credit requirement, which comes from a process for background checking for the purpose of granting a credit at a Dutch bank. It is a medium-sized event log. The third one is traffic fines, which comes from a process to collect payment of fines from a traffic law violation at a local police office in Italy. It is an example of big event log. We define the runtime as the amount of time needed to transform the event logs of 2 parties securely into an annotated DFG. In this figure, we illustrate the observed execution time when varying the number of chunks used in the parallelization. Each bar represents the runtime of the parallel sort in blue and the runtime of the DFG calculation in orange. We conclude that the runtime decreases with increasing the number of chunks due to parallel sorting of chunks. For further explanation, we report the number of processed events per second when varying the number of chunks. We find a consistent improvement for the throughput across all the event logs. We summarize that the proportion of runtime between sorting and DFG calculation differs based on the event log characteristics. For logs with the largest number of event types, the DFG calculations make up the most substantial proportion of the total runtime, as in the increasing size of vectors required to represent each activity due to the bit vector representation, and that makes the computation heavy calculations. The communication overhead is the amount of data transferred between the computing parties during the multi-party computation. The communication overhead gives insights into how much the performance of multi-party computation would degrade if the computing nodes of the parties were distributed across wide area network. In this figure, we observe that the communication overhead decreases with an increase in the number of chunks. Our evaluation has 2 limitations. First, the event logs used in the evaluation are intra-organizational event logs, which have split into separate logs to simulate an inter-organizational setting. It is possible that these logs don't capture the communication patterns found in inter-organizational processes. The proposed technique can handle small to medium-sized logs with relatively short traces, but there may be other characteristics of the event logs that affect the performance of the proposed approach. In conclusion, we introduced a framework that enables 2 or more parties to perform basic process mining operations over their partial logs of an inter-organizational process held by each party. The framework only reveals the queries and high-level log statistics that the parties agreed to disclose. An evaluation using real-world event logs shows that it is possible to compute the DFG with execution times that make this technique usable in practice. The divide and conquer approach provides opportunities to scale out the proposed technique by using MapReduce execution style. However, not to a sufficient level to enable interactive process mining. The approach is not able to handle logs with thousands of traces. In future work, we will combine the proposed approach with differential privacy approaches to noisify the DFG and the output of the framework. An interesting application for the framework is the problem of business process management benchmarks, where an organization is interested in knowing their performance in comparison to the industry standards and other performers. For further discussions and questions, please contact me using my email here. Thank you for your attention.